Okay. Uh, so is it clear? Move dx comma 0 0 0 0. That is the first instruction which I have written to save my carry. Then move ax comma 1 2 3 4, which is considered as my first data byte as 1 2 3 4 into ax register. And second is move dx comma 5 6 7 8. The second data byte 16-bit data. All these are 16-bit data. 16-bit data must be saved onto dx register. Then I have added the add ax comma bx, so that after addition the result will be 16-bit result will be stored inside ax. And if there is no carry, just I need to stop my program using this instruction int03. And if there is any carry, perform inc dx, increment the content of dx by 1, so that dx will be 0 0 0 0 if there is no carry. If there is any carry, dx got 0 0 0 1. Okay, so these are the inputs I have considered, and these are the outputs after addition what I have got in my register. Okay, so ax contains the sum of the addition and dx contains the carry. Okay, so is it clear?
Hello.
Hello,
Mm.
hello,
Sir,
is it clear?
yes, sir. Yes, sir.
Is it clear, everyone?
Yes, sir.
Okay. Shreyasi, is it clear? Can you hear me?
Yes, sir. Hello?
Hello, hello.
Yes, sir.
Okay. Coming to the next program. Next program basically based on the same addition program has been considered, but in different way. Like I have told you that the addition can be using directly using two 16-bit numbers, or assume these two numbers are loaded inside two memory locations, and that memory location should be specified by or pointed by some register. Okay, so in indirect way you can use it, like here. I have considered that source index and destination index, there are two registers. Those can be used to point the source memory location using SI register, and to point the destination register that using DI register, destination index register. Is it clear? If there are two numbers has been loaded in two different memory locations like 2000 and 2002, then I need to call them from the memory location, then I need to add them, and what is the result is generated, I have to send that result into some another memory location which is my destination. Okay, so SI can be used to point the source memory locations, and DI can be used to point the destination memory locations. Okay, so 2000 and 2002, there are two memory locations where 8000 and 8001, these two 16-bit data has been loaded. Okay, now 2000 and 2001, these two consecutive memory locations are required to store this one 16-bit data, because as per the memory space, each memory can store maximum 8 bit of data. Each memory can store maximum 8 bit of data. So if you want to store a 16-bit number, then you need two consecutive memory locations. So here in this case 8000, that is your 16-bit number. Now to load this 16-bit number, you need two consecutive memory locations. That's why this 2000 and 2001, these two corresponding to two consecutive memory locations are required or reserved for 8000 data byte, and 2002 and 2003, these two consecutive memory locations are reserved for 8001 16-bit data byte. Okay, so we need to add these 8000 and 8001. So how can I use the logic? Like DX register, it is used for or used to store the carry portion only. That's why it is initialized as 0000. Then I have considered that 2000 is my first data byte memory address, which will be initialized by source index register, and that source index register is initialized used by this instruction, which is called move x comma within bracket si. So si points this memory location where some data byte is there, and what is the data byte? 8000. So 8000 will be loaded inside x register. Okay, now where is my second data byte? That is in 2002. So I have given 2000 as my initial address, and I need to go to the 2002 memory address. So how can I go from 2000 to 2002? If I add 0002 with the si, then we can come to this position to point the second memory second data byte memory address, which is in 2002 memory location. So si is initialized initially in 2000 memory location. So if I add 0002 with this 2000, what will be the address? 2002. So after addition of si comma add si comma 0002, then move bx comma within bracket si has been considered. So si now points 2002 where some data byte is there. What is the data byte? 8001. That 8001 should be stored inside bx register. So my first data byte 8000 is stored in AX register, and my second data byte is stored inside BX register. Now I have two data bytes into two different registers, which I need to add them. Then you need to use the add instruction, add AX comma BX, and after addition you need to check the carry whether there is any carry or not. Now if there is no carry, what you need to do? You need to just transfer the content from AX to certain memory location. So now to transfer your result from some register to memory location, you need to initialize that memory location first. Otherwise, Microprocessor can't recognize where you need to store it. So that's why I have given here move di comma 3000. Now 3000 is my destination location where I can transfer my result from accumulator or AX register. So that's why initially it was written by this instruction move di comma 3000, then move within space di within space within bracket, it is considered as di comma x. Then what is your result inside this ax register? That must be stored inside this memory location, which is pointed by di register, that is 3000 memory location. So your accumulator result must be stored inside 3000 memory location. Okay, so that is my sum part, which will be stored inside 3000 memory location. And what about the carry? So if there is any carry, if there is no carry, just dx will be 0000, and that will be saved onto next memory location. Now again, x contains 16-bit result. So to store that 16-bit, you need two consecutive memory locations, which is 3000 and 3001. Then to save the carry, you need next memory location, which is 3002. So I am here in 3000 memory location, and it is the 3002. And how can I move from this position to this position? If I add 0002 with the di, then I can easily move from this level to this level. In that case, I need to add di comma 0002. Now 3000 was first initialized by di. Then if it is added to 0002, then the address will be considered as 3002, where I can put my carry portion into 3002 memory location. Okay, so if there is no carry, this will be executed in this way. If there is any carry, then what you need to do, you just increment the content of dx by 1, so that dx will be 0001. Then this will be saved in this way, and it is executed sequentially one by one. The last instruction, which is int 03, to stop my execution. Is it okay? Is it clear, everyone? Is it clear?
Yes, sir. Yes, sir.
Yes, sir.
So that is the addition. So coming to the next one, which is the subtraction. The same thing you can perform it using the sub instruction. You have addition instruction, add instruction, you have sub instruction. In case of addition, you need to consider the carry. In case of subtraction, you need to consider the borrow actually the carry. Okay. Okay, Vitanu, can you ask me something? Do you have any queries? Vitanu, do you have any question? Hello? Hello, Vitanu? Do you have any queries, any question? Okay. So in subtraction instruction, I have considered the dx as 0000 to store the borrow part, and move x comma 6000. So I have taken the largest number inside ax register and the smallest number inside bx register, so that there will be no carry. If it is considered as 2000 into ax and bx contains 6000, in that case the subtraction must have some borrow, because I have considered in that case I have considered the smallest number into ax and I have considered the largest number into bx. And what is happened in sub ax comma bx, subtract the content bx from ax. So that is the destination and it is the source part. So source always subtracted from the destination. If I have considered this one as move bx comma 6000, move cx comma 2000, and then sub bx comma cx, what happened? So bx minus cx and the result will be stored inside bx. Here also sub x comma bx means x minus bx and the result will be stored inside ax. Okay, so after that I need to check whether there is any borrow or not. So there is no carry or no borrow, the same thing, or no, is there any carry or any borrow, that is the same thing. So I have used the JNC. If there is no carry or no borrow, I just need to stop my execution, and if there is any carry means any borrow, that will be incremented by 1. Dx contains the borrow part. So I have considered the x as inputs are taken as 6000 into AX register, 2000 into BX register, and 0000 has to be considered as into DX register. And the output is considered as AX contains the difference and the DX contains the borrow part. Okay. So addition subtraction is completed. Then we go to the multiplication. Now, how can you perform the multiplication? So, in case of multiplication, there are certain rules you need to follow every time. Always you need to consider the first number into x, the 16-bit number into x, and second number is from any register, like you can use bx, cx, whatever. So this multiplication is basically between two 16-bit numbers, between two 16-bit numbers. Okay, so if any multiplication is performed between two 16-bit numbers, the result must be more than 16-bit, 32-bit. So automatically after multiplication, the result will be 32-bit in size. So your 32-bit can be stored in this way. Your 16-bit will be always stored inside X register, and upper 16 bit will be always stored inside dx register. So combinations of dx and ax, it creates one 32-bit result of 16-bit to 16-bit multiplication. Okay, so here I have considered 4000 and 2000 as my two 16-bit numbers which I need to multiply, and using this instruction, first I need to store the first number inside ax register and second number inside bx register, and then bx, multiplication between the content of ax and the content of bx, and the result will be stored in ax and dx register. And next is the stop the execution using int03. Okay, so it is according to our lab, that's why we have used the int03. And theoretically you can write it as int03 or halt, anything. Okay, no problem, but in case of our lab, according to our kit manufacturer, only int03 is applicable. Okay, that is compatible with the trainer kit. So that's why int03 is written here for all these programs, because these programs we need to executed in future using trainer kit. Okay. So inputs has been considered as ax equals to 4000 and bx equals to 2000, and output is considered ax that contains the lower 16-bit number and dx that contains the upper 16-bit number. Because if 4000 into 2000 can be multiplied, your result should be 08000000. That is in 32-bit size. Okay, 32-bit form. Your 32-bit size result can be stored in this way. Lower 16-bit will be always stored inside AX register, and upper 16-bit will be stored inside DX register. So both AX and DX contains the total 32-bit result. Okay. Next, coming to the division program. Division program, here you need to consider the 32-bit number divided by 16-bit number. Okay. First, I will discuss this 32-bit divided by 16-bit. Then I will discuss the 16-bit divided by 16-bit. Okay. Let's clear this concept, how 32-bit will be loaded inside some register and that must be divided by some 16-bit content. Okay. So my 32-bit number is 23454567. It is given inside this box. Okay, 32-bit number is considered as 23454567. So your all registers are 16-bit in size. So now how can you store this 32-bit number at a time? So that's why you need two registers, 16-bit register. I have considered here AX and DX. So always you have to remember these rules in multiplication and division. AX and DX must be used. Okay, no other register can be used as your first number to store it. Okay, always you need to initialize AX and DX. So here also your first number will be stored inside AX and DX register. If you have 32-bit, then lower 16-bit will be always stored inside AX register and upper 16-bit will be stored inside DX register. But if you have only 16-bit number, then upper DX will be taken as 0000 and lower 16-bit will be your actual 16-bit number, which must be divided by some 16-bit value. And that 16-bit value is here I have considered as 4111. Okay, so that is my number which will be divided by this number. So this number can be taken inside any register, that is either into BX or into CX. I considered here as CX, that is used to store my second number. Then I have used the deep CX instruction, and deep CX instruction means AX DX divided by CX. AX DX is a combination of two 16-bit number, it's a 32-bit number. So your 32-bit number must be divided by a 16-bit number. Okay, so deep CX contains the 32-bit number divided by 16-bit number. Okay, and when this division is performed, how the result is being stored, your result automatically get stored inside AX register, that is the quotient part, and DX contains the remainder part. Always in any division program, your quotient value must be stored inside AX register and your remainder value must be stored in DX register. Clear? your question value must be stored inside AX register and your remainder value must be stored inside DX register. Is it clear? So always you need to take your first number inside AX and DX register. If you have any 32-bit number, then AX DX can be used, and if any 16-bit number, then your 16-bit number will be stored in AX, and by default DX can be treated as your 0000, or you need to initialize it with 0000. Okay, suppose here I've given an example. Write down the example. Do you have pen and paper with you? You can write down the example. Also 16-bit by 16-bit division. 16-bit by 16-bit division. Okay, take one number, 16-bit number, as 0004, 0009. Take it as 0009. Okay, 0009, and uh, and CX contains, CX equals to 0002. So here you need to divide 0009 using 0002. So 0009 divided by 0002. So 0009 must be stored inside AX using this instruction move AX comma 0009. In that case, you don't have any another 16-bit number. Okay, so that's why you need to write it as move DX comma 0000. So what you have written from the initial position, move AX comma 0009 and move DX comma 0000. Then move CX comma 0002. Then div CX. Then INT 03. I repeat from the first instruction, move AX comma 0009, move DX comma 0002, move CX comma, move AX comma 0009, move DX comma 0000, move CX comma 0002, and then div CX, then INT 03, and you can get the result inside AX as 0004 as quotient, and DX equivalent to 0001, which is the remainder value. Is it clear, everyone?
Sir?
Hello, is it clear, everyone, up to this much?
Yes, sir. Yes, sir.
Then go to the next program, which is the series addition. Now, what does it mean? Series addition means there are several numbers, 5 numbers or 10 numbers or 100 numbers are there. You need to add them one by one, and you need to store the result in some register or memory location, and store the carry also in some register or memory location. So here we have considered 5 numbers. These are stored in 5 consecutive memory locations in this way. My numbers are 16-bit numbers are 8000, 8001, 8002, and 8003. 4 numbers are present, and these numbers are assumed stored in some memory locations, and the memory locations are 3000. So this 3000 memory location and 3001 memory locations, 2 consecutive memory locations are reserved to store 8000 data byte, 16-bit data byte, and 3002 and 3003 that is to be used to store 8001 database, 16-bit database. 3004 and 3005, these 2 memory locations are required to store 8002 16-bit data, and 3006 and 3007, these 2 memory locations are reserved for 8003 database. Clear? So for to store the 4 16-bit numbers, you need how many memory locations? 8 memory locations from 3000 to 3007. Okay, so we have 4 numbers, then what you need to be considered, the most important thing you have to consider the counter. Okay, if there are more than two inputs are involved, then you always have to use the counter concept. Why? Because how many times your such operation will be repeated, you don't know. It based on the counter value. If there are four numbers, so how many times your addition will be performed? You need three times addition. Okay, you have four numbers, you need three times addition. Why? Because first this 8000 and 8001 will be added, then what is the result that will be added to the next one? So this is the second addition, and what is your result that will must be added to the last number, that is my last addition or the third addition. So how many times this addition will be repeated? It based on your counter value. So your counter value must be stored in some register as 0003. That's why I have taken that move cs comma 0003. Okay, and move dx comma 0000 means I need to store my carry in some register, which is dx in this case. And I have considered my starting memory location as 3000. That's why it is considered as source index, because these are my source memory locations. So that's why source index register must be initialized to point these memory locations one by one. So move si comma 3000. Now from 3000, the first data bit 16-bit data will be stored into AX. So if move AX comma within bracket SI is given, that means your 16-bit data, which is 8000 in this case, this 8000 must be stored inside AX register. So my first data byte is loaded in some register. So what I need to do, I need to add the second number, but where it is in next consecutive memory location. And how can I go to the next consecutive memory location? If I add some displacement to the source index register address. So it is in 3002. My second data bit is present in 3002 memory location. So that's why 0002 must be added to the 3000 memory location. So according to this structure, what does it mean? That means SI now points 3000 plus 0002, which is 3002. The combinations of these two, addition of these two numbers, 3000 and 0002 will be 3002. Where my second data byte is present, I need to transfer that data byte from this memory location to BX. So my first number is already stored inside AX and second number is loaded inside BX. So now I can add them. And how can I add them? Using add instruction, add AX comma BX, and then I need to check whether there is any carry or not. So if there is no carry, what I need to do? I need to operate the counter part. And if there is any carry, I just increment the content, then I need to operate the counter part. But here, one interesting or the beauty of the instruction set or powerful instruction set of 8086 microprocessor is, in 8085 microprocessor, you need to decrement if you want to access your counter operation until zero condition. How can you implement this logic? Always the content of that register, counter register, will be decremented by 1, and until this will be decremented by 1 until it reaches zero condition. So you have two instructions, one is DCR and another is JNZ. Okay, but in case of 8086, you don't need to use a separate instruction for decrementing your counter value. Okay, so there is a string instruction, there is a loop instruction which is used directly, so that automatically CX get decremented by 1 every time until it reaches zero condition. So when loop is executed, microprocessor automatically decrements the content of C register by 1 until it reaches zero condition. If there is no zero, it again moves to such level and repeat this process. Okay, so this loop will be continued until your CX register gets 0000. Okay, so if there is no carry, you need to perform the loop operation. If there is any carry, you need to operate certain anything else, and extra instruction will be executed. Then you need to come to this loop execution. Okay, so loop will be executed up to executed up to certain level until your CX gets 0 0 0 0. Yeah, and when CX gets 0 0 0 0, it falls through this loop and go to the next instruction to stop the execution, and that means you have completed your addition, and already the result will be stored inside some register. Now after addition, according to this instruction, what happened? Addition between the content of X with the content of BX, and the result will be stored inside X. So your 16-bit result must be stored automatically inside X, and your carry for this addition will be saved onto BX register. Okay, now you can move this register from, you can move this result from this register to any other memory location using different instruction, using DI instruction. Okay, so that is the different thing, but here is the logic, simple logic. If there are 4 or 5 or certain numbers are present inside some memory location, how can you add them, how can you store the result, and how can you store the carry also. Okay, which is the extra bit from your 16-bit result. Is it okay, everyone? Is it clear up to this much?
Yes, sir.
Do you have any queries up to this one? Do you have any queries up to this one?
No, sir.
Okay, so shall I
No, sir.
proceed to the next program? Okay, so that is the next program, which is a very interesting program. That means you have to find out the largest number from the array or the smallest number from the array. Now, array means your some data bytes has been there in some memory locations, and some memory locations from there you need to find out which one is your largest value, or which one is your smallest value. Okay, so now to find out this largest number or smallest number, you have one such instruction, which is compare instruction. Is it clear? Compare instruction, CMP, compare. Now compare instruction can be executed in several ways. Last I have discussed about the compare instructions in case of different types of instructions. You can compare a particular 16-bit data with accumulator content, or you can register to register comparison can be there, CMP AX comma BX, or you can compare the register content with some memory location content. Okay, here I have used the memory location content must be compared with the register content. Okay, so so we have 4 numbers in these memory locations: 3000, 3002, 4, and 6. 4 numbers are stored. Now among these 4 numbers, we need to find out which one is my largest number, and which one or this is the largest number, so which one is my largest number. Okay, so your first instruction should be your initialization instruction for source memory location, where your first data byte has been stored. So that's why I move SI comma 3000, source index can be initialized with 3000 memory address. Then move CX comma 0003. Why? What is the function of this instruction? This is my counter register, or that is my counter value, because we have 4 numbers. Now among these 4 numbers you need to compare it. So if first 2 numbers are compared first, then what is your largest number is find out between these 2 numbers, that must be compared with the second one. This is your second comparison, and what is given inside this one, the largest number, that must be compared with the last one. So third comparison must be there. So how many compare instruction will be executed, how many times? There will be 3. So that's why my counter value will be 3. Is it clear? Then move AX comma SI. The first value which is stored inside 3000 memory location, which is 8000 in this case, that 8000 data will be stored inside AX register. So AX contains the first data. Now where is my second data? Second data is in 3002. So now microprocessor points 3000, and how can microprocessor go to 3002 if 02 is added to 3000? So if 3000 and 02 are added, so this becomes 3002, and it points that contained 1000. This is the 1000 which is stored inside 3002 memory location. So that content directly compared with the first content which is loaded inside AX register. Okay, now after comparison, what happened? There will be three conditions. Three conditions will be arised. Uh, what are the three conditions? First one, if accumulator content is greater than the memory location content, means the SI content of SI, or AX is less than the content of SI, or AX is equals to the content of SI. Okay, so if there is no carry, if there is no carry, means your accumulator content is higher or the largest one. Okay, now what happened in this case? CMP AX comma within bracket SI means AX minus this content of SI. Okay, so what is the content of AX? That is minus the content of SI. So always this content of SI must be subtracted from the AX, but it doesn't generate any result. It only creates three conditions. It only creates three conditions. Okay, that is the difference between a subtraction and compare instruction. Subtraction always gives the result. It stores the result inside some register, but here compare instruction, it subtracts, but it doesn't generate any result. It only creates certain conditions. Three conditions has been arised: A greater than B, means a accumulator greater than the content of SI, accumulator is less than the content of SI, and accumulator is equivalent to the content of SI. So if there is no carry, obviously the accumulator content is the greater one or the largest one. Okay, so if there is no carry, it just go to the loop, so that your CX must be decremented by 1, and if it is not 0, again this addition, this add SI comma 02 will be there, because last SI contains is 3002 and my next data is in 3004. So if 3002 and another 2 is added, then I can go to the next memory location, which is my 3004, and in this way the next data byte must be compared with the last largest value. So that is if there is no carry, and if there is any carry, so if there is any carry means the content of SI is my largest one. So always you need to remember one thing. In case of largest value, to find out the largest value or to find out the smallest value, always you need to store the result in accumulator. Try to transfer the content. Try to save the result, means the largest value if you want to find out largest one, and if you'd like to find out the smallest one, your result must be always stored inside AX register. Okay, so if the result is already in AX register, no problem, but if there is if the content is in the largest number or smallest number, your result is in anywhere except accumulator, you must transfer the content into accumulator, then perform another operation. Okay, so if there is no carry, no problem, my largest value is already stored inside accumulator. But if there is any carry, that means the second content is my the largest one and the content of accumulator is the smallest one. So I need to transfer the content from the second one to the accumulator, and then after that I need to operate the loop instruction. Okay, so that my CX count, the counter value which is stored inside CX must decremented by 1, and it will be decremented in such way until it reaches 0 condition, so that when it goes 0, CX gets 0, my operation has been completed, and I can easily find out what is my largest number, which is always stored inside accumulator or AX register. If it is not there, you need to transfer it. Okay, but your result must be stored inside AX register. Try to implement this logic always to find out the largest one or the smallest one. Is it clear, everyone?
Yes, sir.
Do you have any queries, any doubts?
No, sir.
Sure. then go to the next program, which is the block transfer program or copy paste program. Actually, you need to shift a block of data from one memory portion, from one portion of your memory to the another portion of your memory. Okay, you just copied a file, just like you have copied one folder or any file from one position to another position. So that means copy paste. So it's a one type of copy paste program. That means block transfer program. So transfer the block of data from one portion of your memory to another portion of memory. Clear? Now,
Okay.
now SI has some memory locations, source index, where some data bytes are present. Like in 3000, there is 01, in 3001, 02. So I have considered here the 8-bit numbers. Okay, we all you must notice here I have considered the each data byte as 8-bit data byte. Okay, 8-bit, not 16-bit data byte. You can consider it, but I have considered here 8-bit data byte. Now that 8-bit data byte is to be shifted from this memory location to this memory location. Okay, so I need to transfer the whole block of data 01, 02, 3, 4, 5 into another memory location, which is in 3050, 3051, 52, 53, 54. So these 3000 to 3004, these memory locations are my source memory locations, and from 3050 to 3054, these are my destination memory locations. Okay, so that's why source memory locations can be always initialized by source index registers, source index address, and and destination memory locations always can be initialized by DI. Okay, destination index. Now there are 5 data bytes. So how many times this operation will be carried out? Like first number will be transferred from 3000 to 3050, then 3001 to 3051, then 3002 to 52, then 3 to 53, then 4 to 54. So how many times the operation will be performed? 5 times. We have 5 data bytes. One by one, 5 data can be moved from one position to another position. So what will be your counter value? 5. Okay, so after each operation, your counter will be automatically decremented by 1. If your counter reaches 0 position, that means whole block of data, means every data byte is transferred from one position to another position. Okay, so that's why my counter value must be 5 in this case. So I have considered move cx comma 0005. The counter value must be 0005, so that every time the 005 will be decremented by 1 until it reaches 0 condition. And move SI comma 3000. SI, the source memory locations are initialized by SI, and 3050 can be initialized by DI. These are the destination memory locations. Okay, CLD. Now actually this program is based on or using string instructions. Last day I have discussed about the string instructions, and what are the string instructions? That is move SB, repeat. These are the string instructions. Okay, string instructions, and these instructions are used. It has some flexibility to use this. You don't need to consider every byte one by one to transfer. Okay, automatically whole block will be transferred after this, so that automatically my counter value will be decremented by 1. Now whether your memory locations will be incrementing order or this will be in decrementing order, that must be depends on your flag register. Which flag register? The direction flag register. That's why you have to you have certain flag manipulation instructions like CLD, clear direction flag, means you have direction flag. Now if direction flag is 0, your memory location will be goes into auto increment mode. Is the first memory location if 3000, then go to the next memory location as 3001, then 3002. So 0, 1, 2, 3, 4, 5, in this way it is in incrementing order. But if your direction flag is 1, that means your memory location should be implemented in auto decrement mode. Means first 3009, then it goes 3008, then 7, 6, 5, 4, 3, 2, 1, 0. This is called in decrementing order. Okay. Now, according to your program requirement, so I need to store my 01 data, which is coming from 3000 and goes to 3050. Then come to the second data byte, which is stored in 2001. So continuously, I need to go it from 3000, then 1, then 2, 3, 4, 5, 6 in this way. If there are some data bytes are present. So always I need to go in some incrementing order, and if I need to follow the incrementing order, then I need to make 0 or reset the direction flag, and that is called the clear the direction flag. Clear means to set it 0, and set the direction flag means to set it 1. Okay, so if direction flag is 0, we can move into auto increment mode. If direction flag is 1, we can move into auto decrementing mode. So here we need to go into auto incrementing mode. So that's why we need to implement it using CLD, clear direction flag. CLD, clear direction flag. So clear the direction flag means direction flag is 0. Now if direction flag is 0, we can move into incrementing order. Then the next instruction is REP, repeat. Now repeat the process. Which process? Always repeat must be given in front of actual instruction. Means move SB, move string byte, move string byte. Now it's a one string of data. 1, 2, 3, 4, 5. It's a one string of data. Move the string bytes. Bytes means it's a 8-bit of data. So 8-bit equivalent to 1 byte. So that's why it is called string byte. So move SB represent move this string byte into some another position. Okay, so this will be repeatedly performed. So repeatedly perform until your CX gets decremented by 1 at which is 0 condition. So repeat the process. Which process? Move the string byte. So repeat the process of moving operation of string bytes until the CX register gets 0. The whole process will be repeatedly performed. Okay, so when CS gets 0, it stops the execution and go to this levels int03, so that your complete string of block of data will be transferred from one position to another position. So this is called block transfer using string instructions, and the string instructions are here REP, repeat, and move SB. So itself repeat has no function until it is written with some another instruction. Okay, suppose there is no move SB is there. There is no move SB, only repeat is there. It doesn't anything mean. It is meaningless. Okay, you need to repeat such a process until the counter value gets decremented by 1 and it reaches 0 condition. So always you need to give a such condition. Now if, okay, one thing, I have used the 8 bits. Okay, so 8 bits number. If I need to use the 16-bit numbers, how can I move it? Then in that case, everything will be same. Like here, the corresponding locations will be incremented in this way. 3000, then 3002, then 4, then 6, then 8. Here 0, 2, 4, 6, 8, and this will be 0001. This will be 0002. This will be 0003, 0004, and 0005. In this way, this can be transferred into new block of memory where 3050 is there, then 3052, then 3054, then 3056, and 3058. The last memory location. Everything will be same in instructions. Only this move SB, in spite of this move SB, this will be move SW. Move SW means string words. Words means your 16-bit number. Byte means 8-bit number. 8-bit equals to 1 byte. That's why it is called string byte. And if you have used 16-bit number, consecutive 16-bit numbers, then you have to use move SW, which is called string word. Okay, word means 16-bit number. Okay, that is the difference between the 8-bit operation and 16-bit operation in case of block shifting. So, is it clear, everyone? Tell me, these are the basic programs you must clear with.
Yes, yes, sir.
If you have any doubts, any queries up to this much, you can ask me. But you have to
Sir.
clear this concept. Every program, these are the basic programs. Do you have any question regarding this program?
No, sir.
Do you have any queries relating to other means the last day uh, discussion? Do you have any queries, any instructions? Because I have used lots of instructions in these programs, all these programs. Any instructions you are not familiar with, or you are confused about the instruction functions? Anyone? If you have any confusion, you can ask me.
Sir.
Yes, please. Yes. CLE, Itanu. Question G. Multiplication program. You have not understand this multiplication program. You have not understood. And Vitanu CLD. CLD, clear direction flag. Uh, this is for Vitanu. CLD, what is the function of CLD is clear direction flag. Means you have 9 flags total in 8086 microprocessor. So individual, every flag has certain conditions. Based on this, the flags will be affected either 0 or 1. But there are 3 flags uh, which are used to control the operation of the machine. Okay, so every time microprocessor performs certain operation using the memory address. Okay, without memory address, no operation can be performed. So your memory address, like if you want to access any data bytes from data segment register, whether your data will be suppose lots of data bytes are there in this way. Here I have given an example. 3000, in this 3000 memory address there is 01, then 02, then 0345 in the memory location. Now, if you want to access the first data byte from 3000 memory address from this address, and you need to go to the second memory address in this way, then go to the third memory address. So actually you are going into incrementing order: 0, 1, memory location 3000, then 3001, then 3002, then 3003, then 3004, then 2005. In this way you can go to the go in the incrementing order. Okay, but if your requirement is to access the first memory location, in this case from 2004, then you need to access the memory location 3003. So how can you go to this one? Initially it is given 3004, then you need to go to the 2003, then go to the 3002, then 3001, then 3000. So it is in decrementing order. So either you can go in incrementing order or you can go into decrementing order. Yeah. So if you want to go or to access your data bytes in incrementing order, incrementing memory location, you have to reset your direction flag. Reset means to 0. Set is 0. Reset means 0. Set means 1. So you have to reset it means actually it is clear. So কোনো কিছু clear করা মানে it's a 0. Nothing is in this. Okay, and set means 1. So here 0 করা মানে কোনো এখানে ডিরেকশন ফ্ল্যাগে 0 করা মানে we increment অর্ডারে যাচ্ছে। Okay, so you have to perform the execution in incrementing order. Now to process it in incrementing order, your direction flag should be cleared. So that's why CLD instruction is used, because I need to access my data bytes in this way, not in this way. Yeah, it goes always in this way. That's why it is in incrementing order. That's why I have used the CLD instruction. And REP, repeat instruction, actually I need to repeat the process of this shifting of this data byte. So move the string bytes. String byte means move this data from this position to this position, then this position to this position, then third data from this position to this position, this position, this position, this position. So this is repeatedly performed. That's why REP is used. If REP is not there, only move SB is there, so only first data will be moved from this position to this position. It is not repeatedly perform this operation. So you have to perform this one. First this data will be moved from this position to this position, then second data will be from this position to this position, up to until the CX, your counter value which was initialized as 0005 gets 0. This whole process will be continuously performed or repeatedly performed. That's why repeat instruction is available. And INT03 is to stop your execution. Okay, just like in case of 8085 you have used RST3, that was a software interrupt. In spite of RST3 you can use halt also, but as per our laboratory kit, okay, RST3 only compatible. Here also you can use INT03 or HLT halt, but as per our lab, means our trainer kit manufacturer, INT03 is compatible. Okay, for practical purpose, INT03. Multiplication program is this one, where I have loaded two numbers in two registers, then I need to multiply them, and when I have multiplied, my result is automatically stored in AX register and DX register. AX register holds the lower 16-bit result and DX register automatically holds the upper 16-bit result. If you like root of 16-bit কে যদি আমি মাল্টিপ্লাই করি তাহলে আমার রেজাল্ট মোর দ্যান 16-বিটই হবে, তাই তো 32-বিট হবে। বাট তোমার এখানে সব রেজিস্টার ইউ হ্যাভ অ্যাক্সেস ইট অ্যাজ 16-বিট রেজিস্টার, কোনো 32 রেজিস্টার নেই, 32-বিট রেজিস্টার। তোমার রেজাল্ট যদি 32-বিট রেজিস্টার কিভাবে সেভ করবে? In that case you have to use the two registers, and by default in 8086 microprocessor architecture the two registers are only DX and AX register to save any 32-bit result in your multiplication. Jump program in copy instruction is jump program? No, jump is yes, you can You can use jump, but there is no need of jump. Why you have to use the jump program, jump instruction? For Prosenjit Das, you can't use jump instruction here. Okay. Anything else from anyone? Any extra? Any other question from previous day lecture? Do you have any queries? Any question from previous day lecture? From previous day lecture, do you have any queries or any question?
No, sir.
Okay, then that's all for today. Okay, we'll discuss the next programs. The next different other programs are available. Okay, we'll discuss the next programs on next class, and see you on Thursday. So that's all for today. Thank you all.
Santu, sir.